Hello everyone, my name is Sheikh Siraj. I am from ECE department. Today I am explaining about a new approach parallel to diagonalization symmetric matching. First of all, we know to symmetric matching. This article about matrix symmetric about its diagonal for a matrix symmetric about its center C centrometric matrix. For matrix with symmetry of the complex number field C hemization matrix. This is the hemization matrix of diagram. So symmetric of a 5 by 5 matrix. In linear algebra, a symmetric matrix is a square matrix that is equal to its transpose formally. Because equal matrices have equal dimension, only square matrix can be symmetric. The enters of a symmetric matrix are symmetric with respect to the main diagonal. So if denotes the entry in the row and the column then. Here fall for all indicates and every square diagonal matrix is symmetric since all of diagonal elements 0 are 0 are 0 similarly in characteristics different from two each diagonal elements of a skew symmetric matrix must be 0 since each is its own negative corresponding object for complex inner product space is summarization with complex valued enters which is which is equal to its conjugate transpose. Therefore, in linear algebra over the complex number, it is often assumed that a symmetric matrix refers to one which has real valued entered symmetric matrix appears naturally in a variety of application and typical numerical linear algebra software makes special accommodation for them. So here example the following 3 by 3 matrix is systematic symmetrically. Like example 1 7 3 1 7 3 5 4 5 this like so basic properties the sum and difference of two symmetric matrices is symmetric matrix. This is not always true for the product given symmetric matrix and then is symmetric if and only if and commute condition like for any integer is symmetric is a symmetric if x is it is a symmetric of if and only it is symmetric. Decomposition into symmetric and skew symmetric equation SV matrix. In square matrix can uniquely be written as sum of a symmetric and a skew symmetric matrix. The decomposition is known as the topological decomposition. Let denote the space of matrix. If donates the space of a matrix and the space of skew symmetric matrix the then and so where does not the direct sum let then notice that that and this is true for every square matrix with enters from any field whose character is different from two a symmetric matrix is determined by scalar the number of enters on or above the main diagonal. Similarly, a skew symmetric matrix is determined by the scalar the number of enters above the main diagonal. Matrix congruent to a symmetric matrix. Any matrix congruent to a symmetric matrix is again symmetric matrix. If is a symmetric matrix, then so is for any matrix. Symmetry implies normality. Normality. A real value symmetric matrix is necessarily a normal matrix. Real symmetric matrix, read it. So here they see say some matrix like what this inner product on denoted by this. So here this now since this definitions is independent of the choice of a basic symmetric is property that depends only on the linear operator a and a choice of inner product. This characterization of symmetry is useful for example in differential remaining main manifold. Another area where this formulation is used is an Hilbert space. So the finite dimensional spectral theorem says that any symmetric matrix whose enters are real can be diagonalization by an orthogonal matrix. More especially for every real symmetric matrix there exists a real orthogonal matrix such that is a diagonal matrix. Every real symmetric matrix is thus up to choice of an orth, ortho what is this this choice of an orthonormal basic a diagonal matrix. If an or real symmetric matrix that commute the then the then they can be similarities diagonalization. Diagonalization. Here there exists a basics of such that every element of the basics is an engineer vector for both and every real symmetric matrix is a emission and therefore all its eigenvalues are real. In fact, the eigenvalues are the enters in the diagonal matrix above and therefore is uniquely determined by up to the order of its enter. Essentially, the property of being symmetric for real matrix corresponds to the property of being Hermitian for complex matrix. So here a complex symmetric matrix. A complex symmetric matrix can be diagonalized using a unitary matrix. Thus, it is a complex symmetric matrix. There is a unitary matrix such that is a real diagonal matrix with non-negative enters. This result is referred to as the autonomous Takagi factorization. It was originally proved by Leon Otto in 1915 and Teiji Takagi 1925 and rediscovered with different proof by several other mathematics. In fact, the matrix is Hermitian and positive semi-defined, so there is a unitary matrix such that is diagonal with non-negative real entries. Thus, is complex symmetry with real writing with and a real symmetric matrix. Thus, since and commute, there is a real orthogonal matrix such that both and are diagonal setting a unitary matrix. The matrix is complex diagonal free multiplying by a suitable diagonal unitary matrix which process unitary of the diagonal entries of can be made to be real and non-negative as desire. To construct this matrix, we expose the diagonal matrix as the matrix we seek is simply given by clearly and deserve. So we make the modification since there is where are the eigenvalues of the consumed with the singular values of. Note about the eigen decomposition of a complex symmetric matrix. The Jordan normal form of a may not be diagonal, therefore may not be diagonalized by any similarity transformation. So this is our topic. So thank you all of you.